Hi guys. Okay, everything's fine, I guess. Okay, so this is the link to the contest. This time at least I'm starting at 0-0. Yeah, let's see how it goes. Oh, why is this not full screen? Okay. Uh, trippy, tropy, something. Uh, three strings, first letter to form. Okay, that's it. Wow. Okay, I forgot this was div 4. This is supposed to be too easy. So you have test cases, you have, I guess, three strings. I guess speed is the only thing that matters in problems like these. Ah, I could have written a loop. Too late now, I guess. Okay, but this should work. Okay, one down, I guess. This was just implementation. I really don't want to explain anything because, I like to explain logic instead of implementation, I guess. Okay. Running, accepted, I guess. Okay. Now, burrito, bendito, all of these rhyming or what? Okay, number line. Okay, exactly one. Okay, I don't get it. Okay, M is smaller than N, right? I guess we just need fewer houses to be infected. Two less houses, so we can just always subtract that value from R. Hmm. Exactly. Okay. For B, again, we have test cases, and then we have N, M, L, R. Okay, so I think one correct answer is just, I've become really bad at typing. So I think one correct answer is to just leave L as it is, and then from R we can subtract the difference of N and M. Okay, let's see. -2 0 works, I guess, and 0 1 also works. This is correct. Yeah. Okay. So I think first 3 4 problems of diff 4 are like too easy, and after that maybe the real stuff begins. It will be really funny if I get wrong answer on this one. Like I'm belittling the problems a little, you know. I think it's really hard to pronounce any of these problem names. I want to see if it's. Let's move on to the next problem. Okay. 2n elements. Okay. Permutation. N cross n grid. Okay. Pi plus j. Okay. Okay. Right. I think it is. Oh, wait a second. 1 plus 1 is 2, 3, 4, 5, 6. Yeah, I think we just go like this, and then the remaining element is the first element. Ah, it's not that. Oh, wow. Wow, okay. Ah. Mm. Oh, it started from house 0. Right, I think I didn't read this part. Okay, so since it started from house 0, so like we need to decrease it by n minus m, and then um, let's say how much can we decrease r. It is minimum of the total decrease and the value of r itself. So we'll just do r minus equal to r decrease, and then decrease also minus equal to r decrease, right? Now if like whatever is left, that is now l decrease. Int l decrease equal to whatever decrease is left, so we have to decrease that. We'll just do l plus equal to l decrease, and I think now we're done. Oh, sorry, we have to print ln. Okay, yeah, works. You should read these problems carefully. Okay, so permutation, blah blah blah. Then okay, let's start it from the beginning because yeah, passcode. Yeah, so I think we just go like this. So like this one is 2, 3, 4, and then 1 is remaining. Okay. So the easy way to do this is I think we take n screen and okay, we have the inputs, I guess. Actually, this is G, not P. Let me rename that. Right. Why did I name it D? This is G. Okay, now my answer is this permutation of n. I can fill the remaining elements maybe like this, or like let's say oh, it is size 2n. Okay, so I can just iterate it like this, or maybe even like this, right? Okay, p curve plus plus equals, I guess, g 0i, and then let's fill some more elements like this. So p curve plus plus equal to g of, I guess, n minus 1. No, I n minus 1. Okay, I think that will work. Now we need to know the one element that's not present. So we can do set in s and then fill it with all the elements from 1 till 2 into n. Okay, and then erase them here. like this, and then there's just one element remaining that that should go in the first place. Now I just have to print the permutation. Okay, nice. Okay. Tung Tung Sahur. Which country people have made this round? Oh, sorry, this is the wrong round. Where are they from? QED. New York. I don't know. But yeah, they got really weird names. Okay, accepted. Right, so you have two drums. Hit on the left can be recorded as L and then R. Okay. Screenforces rule. Am I recording? Okay, yeah. I was just worried I didn't hit the record button. L L L R R R. Okay. Okay. Right. I think it should be not that hard. Right, so every L can be LL. Okay. I think we just need to count how many L's are there and then how many R's are there. And we can maybe, I think, double them. This is again an implementation problem. Like, we just have to make segments of these. Like, this is 2L and then 1R, then 1L, 1R, and so on. And this is 3L and 1R and so on. So 2 can become up to 3, like 2 can go up to 4, and minimum it has to be 2. So I think something like that can be done. It shouldn't be too hard. Yeah. So we get 2 strings, P and S. Okay. I think the first element has to be the same. So if P0 is not S0, then I think it's no. Okay. I think otherwise we just need to make those things. Yes. Right. So let's do it for P. Right. Actually, let's just do. Let's start with the second character actually. Okay. Now, right. If I guess pi is not equal to pi minus 1, at this point we just put counts dot pushback count, then set count again to 1. Otherwise we can just increase the count, right? Then once we come out of this loop we can just put this again, right? So this we have done for P. We have to do the same for S, but in a different vector. So to make this easy, I'll just wrap this whole thing inside a function, inside a lambda function. Something like get counts I think this works, and then we just return counts. Semicolon. I think if this compiles, this will be correct. Sometimes you write code that is correct if it compiles. I'll just say vi count p equal to get counts of p, and vi count s equals get counts of s. We have both counts, and I think the number of elements have to be same. So if size of count p not equal to size of count s, then we just say no, not possible, right? Because like the contiguous sequences of else and ours, like the total number of those should be equal. Now we go to each of them one by one, so I'll just do let's take the size of this, right? So I'll just iterate on that. Now let's take the corresponding element from both of these. Now if y is smaller than x or y is greater than 2 times x, because you cannot lose any element, and you cannot go more than double. So in those cases it is a no, right? But if everything works fine, then it has to be a yes. Let's see. As I said, if it doesn't compile, so we don't have the size macro, I'll just define it. Size v is, I think, int of v dot size. Oh, okay. Let's go. What? Oh, this has to be string. Works. As I said, if this compiles, this will be correct. Okay. But we're not sure if it's correct. That's the funny part. Maximum value of XOR between consecutive elements? No, these are not consecutive. Oh. Oh, sum of XOR with a particular element. Okay, so yeah, D was correct. Sum of XORs with a particular element. We want the maximum value of that. Right. Can we calculate that for every element? I think we can do it independently for every bit. So we just need for how many elements this bit is high, and then yeah, I think that's it. So if we take XOR with that, so for every bit we need how many elements are high and then how many elements are low. I think this one I should explain, but I'll do after solving. Yeah, because the first four were like anything too easy. This. Okay, I think that should explain this previous one as well. Okay. Oh, why is this? Why is there a hello here? Oh, it was hello folks. Yeah, but anyway. So in this one, it was like, so if you have LR, LLR or whatever, so what can happen is, this L can either stay L or be LL. This R can either stay R or be RR. And these two L's combined, they can either be LL or 3 L's or 4 L's, but never 5 L and never 1 L, right? And then this R can be R or RR. So basically, you can break it down into contiguous equal subsequences like this: 1, 2, 3, 4. So first of all, these have to be equal in number. The first element has to be same, and then like so we will denote this as 1, 1, 2, 1, right? Because like this is 1, this is 1, and these are 2, and this is 1. Then if you take the other array, it could look something like LLR, triple L, double R, something like this. So if we make the numbering for this, we can transform it into 2, 1, 3, 2. And what we need is that these two should have equal number of elements. And for every corresponding element, this element should be in the range of, like if this is X, it should be from X till 2X within this interval. So if it's ever smaller than X or greater than 2X, then it doesn't work. And that's what my code for this problem was. So this lambda function just gets this transformation, and then first of all, I just make sure that the first character is same in both strings. If that's true, then the size of the these two sequences has to be equal, and when they're equal, I go to all the elements, and if it is smaller than X or greater than 2X, then it's no, otherwise it's yes. Okay, now we move to the problem E. I will explain it after submitting. But yeah, now let's get into it. So the idea is pretty simple, that we can, just find this value for every element, and this value is pretty easy. Like if you consider that there was only one bit in the element, then like if all the elements are either 0 or 1, you just have to count how many ones are present in the array, and then you can do it. So we just need the bit, like high bit count, something like that. Like, I mean, it's pretty doable. Okay. Okay. Now I can have something like count bits, or maybe just make it a vector. I'll just say bit high count, let's say 32, or I'll just call it, okay. So, okay. Now, let's iterate on the array. Okay, now, okay, and bit high count of I plus equal to, let's shift the element by I bits and take AND with 1. So this will give you the ith bit, right? The bit high count is just like for how many numbers this bit is high, that's it. And total numbers are n, so bit low count is automatically, bit low count is just n minus bit high count. Right, now int answer is, let's say 0. Let's iterate on the elements. Right, now for this element, what will be the value of this? Like for every, like we can, let's say we call it sum equals 0. We can iterate on the bits like this. Okay, now we just need bit high count, I guess. We can say high equals this and low equals, right? Now if this thing is true. So like if this is high, we get low added to the sum, then sum plus equals low multiplied by low, and we shifted by I bits. So it's like 2 to power I multiplied by num low or something like that. Okay, otherwise same thing but high. There are definitely better ways to do this, like slightly better ways to do this, but why should I bother? Okay, so we get the sum, I guess, and then answer is just the max of these sums. I think I am regaining some of my typing speed. It wasn't very much in the first place, so there's not a lot to gain. Yeah, let's see if this is correct. The idea was pretty simple. Basically, you are given an array and they want us to find this sum. Like they want us to find the maximum of this sum for every, like you can pick the kth element and you want the maximum sum of that. But what we can do is we can very easily find this value for every element, and then it's quite easy to get the maximum from there. So to visualize these problems, you should generally assume, like let's say, what if all the elements were in the range from 0 to 1. So what would you do then? So in that case, like especially this is a very helpful trick for XOR problems. Think of this case. Think of this case for XOR problems. Right. So whenever you get a XOR problem, you should think of this case, and this case is actually pretty simple. So you'll see that like if this array just had zeros and ones, so if we take XOR with one of these elements, it will just be the count of ones. Like the total sum will just be the counts of 1, and if we take the XOR with this element, it will just be the counts of zeros. Right now, if we extend this idea, instead of it being from 0 till 1, it can be like from 0 till some 2 to power k, or let's not call it k. What is it? Let's call it capital B. Right. So what you can do is you can solve this problem independently for every bit. So like for B bits, any number can be represented like a sequence of bits like this. Right. So let's say instead of having just one bit, there are multiple bits. What you do is you solve the problem for each bit sort of independently and then add the answers. Right. So mostly that's what I've done. So exactly. So for if you had just zeros and ones, you would keep the count of how many bits are high, like how many ones you have, right? So similarly, I have kept like wow, fuck me. Yeah. So I have kept capital B counts, one for each bit, right? So this is just how many ones are there in the ith bit of the number. And then I simply have low count and high count. So what I'll add is based on what the value of this bit is. And if this bit is high, I will just do 2 to power I multiplied by number of low bits. Otherwise, it will be 2 to power I multiplied by number of high bits. This is nothing but 2 to power I. I'm sorry, 2 to power I multiplied by number of high bits, right? So why am I multiplying it by 2 to power I? So that I can get like the corresponding bit instead of just 0 and 1. I think this also was not too hard. You need to know a little bit about bitwise operations and all. It might be a little hard for beginners, I guess. I'm not so sure how many submissions we're having. 600 submissions, not that bad for the first, first 20, 30 minutes? First 30 minutes, 600 submissions. I think that's fine. So how many we have in A? Oh, 19,000, 19,000, 5,000. I mean, probably people are still struggling with the earlier problems. Like, if you know a little bit about XOR and all, it's not that hard. Am I still recording? Yeah. Okay. So we have. I cannot pronounce the names of any of these problems. I don't know. Is this intentional or what? Like, so some problems are actually a little, recognizable by their names. Like, you can you can have a problem. There's a problem named easy problem. Oh, can't find it here. I can just do maybe a Google search. So there's a problem, let's say ehab and or something like this. So you can see Mahmood, ehab and Zor, right? So some problems kind of get famous just by the name. There are a lot such problems, but the problems from this contest will never be that, because nobody can remember or pronounce these names. But anyway, so I have to Selena gives you 3 integers. That's what the test case is. Okay. And n times m is 0 mod k. Okay. Fine. I don't know how that will help. So we have, okay, n into m is a multiple of k. Fine. So we have to output a grid. Wow. Okay. N cross m. Each integer is from 1 till k. Each integer appears equal number of times. Okay, obviously. So for this, n into m has to be a multiple of k. No two cells that share an edge have the same integer. It can be shown that it always exists if there are multiple solutions binding. Okay, so how does this exist for k equals 2? For k equals 2, I will just do 1 2 1 2 alternate, I guess, and then I'll make it a chessboard for k equals 2. What will I do for k equals 3 though? That's a good question. What do I do when k is 3? Right, 3 is a prime number, so either n or m has to be a multiple of 3. But if we had a composite number, like if we had 6, so it might be possible that neither n is a multiple of 6 nor m is a multiple of 6. It could be like 2 cross 3, so we got 6, right? So 3 4 and 6 exactly. I think this is exactly the case. So what you want is you want to have all the numbers. Okay. Okay. Right. So if I had just started writing like 1 2 3 4 5 6, then again probably wouldn't work. The multiple of 3, like maybe I have to do some prime factorization. I'm not very sure here, but yeah. Let's say if k is 3, so one of those has to be a multiple of 3, and then we just make 3 copies of the same thing, right? So just make the same thing but 3 copies, right? But maybe that won't work easily. So whichever one is a multiple of 3, we can have 1 2 3 1 2 3 1 2 3 1 2 3 2 3 1 and one cyclic shift, right? I still think if we just put them out in this fashion, 1 2 3 4 1 2 3 4 and so on, it would work in some way with like minor modifications. If I just put 1 2 3 4 1 2 3 4 and then 1 2, sorry. If I just do something like this, it should probably work, right? And then so what I can see is if one of the elements is equal, then all of them have to be equal. The only case when they will be equal is this case. If it's like this, right? And in this case, all you have to do is you just have to do one cyclic shift. Sorry, just one cyclic shift. Like let's make this 2 and sorry, just make this 2 3 4 1. In the next line, just go 3 4 1 2 and then 4 1 2 3, something like this. I guess it works. So I'll just put 1 2 3 4 and so on. If the elements are equal, just do one cyclic shift, just print the next element. Works. Okay. Test cases. NMK. Okay. Okay. Just write after this I will just do cur plus if cur greater than k, then cur equals 1. Yes. I also have to store them somewhere. So I can do bbi a n times bi m like this, and do aij equals cur. Okay. Right. Now if I is not equal to 0, so if in the second row onwards, and if my cur equals ai minus 1j, so if they are equal, then all of them will be equal. I'll just do cur plus once so that I can do one cyclic shift. And then this should work, I guess. Okay. Oh, almost missed this part. Although this wouldn't happen, but yeah. This is the same. This works. This works. Sorry, what is this? Wait a second. Do I have more outputs than they have? Oh, sorry. This is the whole thing. Oh, from 1 till 25, they want all the numbers. Yeah, that works. I think should be fine. I don't see a case where this will fail. It's a simple technique, simple logic, whatever. In queue, many 200. Okay, we got 2 tests right. Accepted, yeah. This was pretty simple. How did I come up with this? I think the only case where this case will ever encounter this case is when maybe like this m is a multiple of k, so then the next line would automatically start by 1. But if it is ever not a direct multiple of k, then the second line will automatically be different. So that will work. So if it's equal, then you can just do one cyclic shift and you're still fine. Because again, so if you were in that case where m is a multiple of k, so you can see that k equal elements are fitting here, and if you do one cyclic shift, then also all the elements will happen equal number of times. You can see 1 2 3 4 1 2 3 4. Yeah, that's why it works. Okay, G. That's fine. Yeah, I have to keep making sure that I'm recording it properly, because like one time what I did was I was doing a concert, so I was doing a contest and I forgot to record. So that sucked. But yeah, okay. I times bi. It's the resiness. Okay. Wow. I like this. Empty array, performance. Okay. Reverse, cyclic shift, or append an element to the end. Okay. Okay. They are the ones who do the operations. Fine. I thought we had to construct an array. But anyway. So. Right. And you need to find the readiness, which is this thing. Wow. I think it is pretty, like, the statement is like kind of straightforward. We need you to calculate this value for the array, and we'll keep changing the array. So, deal with it. But how do I deal with this? If we ever do a cyclic shift here, okay, I think the cyclic shift is quite simple. We'll just add the sum of the array to this thing, and so this will become 2, this will become 3, this will become 4, and so on. This will become m plus 1 times bm. So I think we just need to subtract. I think we just need to subtract this m times bm from the answer and then add the total sum once. So I think cyclic shift is easy. You just need the previous answer and the total sum. What about reversing? So I think we should always keep track of both forward answer and the reverse answer, and upon reversal we'll just swap it, and upon cyclic shift we need to update both answers, right? So we need to update both of the answers upon cyclic shifts, and we need to sort of, what do we do? Yeah, we need to keep track of both answers, swap it here, keep track of both here. For this also we have to keep track of both answers. For one answer, you just, for the forward answer, just add m times k, sorry, m plus 1 times k if m is the current length. And for the reverse part, what we will do is we will add the total sum and the element that we're given. So we just need to keep track of the length and the sum and the forward answer and reverse answer. That will work. Okay. So we need to keep track of the length, which is currently 0. The sum, which is also currently 0. We need to keep track of the forward answer, okay, which is also 0, and the reverse answer, which is also 0. Okay, now let's process the queries. Let's take the type of the query as input. Okay, we need to update both of the answers, in this case of cyclic shift. So cyclic shift means, I think forward answer is quite simple. Forward answer equals forward answer plus sum minus len times the last element. We also need to keep track of the last element. We also need to keep track of the first element because we can reverse. Okay, so I think we do something like this. First operation will always be the f equal to 3, so we don't have to worry. Oh, we do have to update the other answers also. The other answer, in fact. So reverse answer will be, if this goes here, what will happen? So currently, I think it will also be something like that only. Let's take the reverse answer, add the sum to it. So that now we'll just have m times the first element that we need to subtract. We need to subtract length times the first element. Okay. For s equals 2, we want to reverse the entire array. So in this case, we swap the forward answer with the reverse answer. Okay. We also swap the first element with the last element. Okay, sum and length will stay the same. Now, if this is 3, we get another integer as input. We have int k, int k. Right. Now let's see how the things will get affected. So our last element will become k. First element wouldn't change, and len will increase by 1. Now forward answer equals forward answer plus len times the last element that we are given, k. What about the reverse answer? Reverse answer will be reverse answer plus, oh, we'll change the sum also, right? So let's do it after this. Sum will get increased by k. Okay. So now I think everything we add sum so that all the elements, the frequency increases by 1, and then we add this element k also. So I think we always have the forward answer and the reverse answer, and for every query we need to print the forward answer. Failed. Oh no, I failed. Wow. 1, 5, 14, 11, 27, 26. Right, I think it's this case that. Sorry, 15. 5, 15. What? Oh wow. Okay, sorry. This is a single test case? No. What's the case? Oh, it's a single test case. Fine. Okay. Anyway. So, at which step did I make the mistake? First 5 are fine. 2. I messed up 2. The reverse answer was wrong. First element might be wrong. So I need to keep track of the first element. It can never be 0, I guess. Yeah, works. If first element equals 0, then first element equals k. Now it should work. Still not working. Okay, now at least this one is fine now. What's the next mistake? This one. Must be a reverse operation again. Fourth from last. Okay. When we reverse it again, I messed it up. Reverse will swap both the answers and swap first and the last elements. I think this might be wrong, maybe, not sure. Mm, it starts with the last element, everything. If you add the sum, the frequency of every element will increase, but the frequency of the first element will become m plus 1, but we have to make it m, so I think this is fine. Len plus plus is fine. Oh, len plus plus before this is fine or not, I'm not so sure. I think these two are correct. This is also correct. You just need to swap the answers. Length and sum won't change. There has to be a mistake here. Now, first element, if it's 0, assign the element. Last element, I assign it. Length have increased. Forward answer, I'm definitely calculated it correctly. This could be the wrong part, right? So the reverse answer, if I have 5 times something, 4 times something, 3 times, 2 times something, if I add the sum, this is also right. Actually, this is right. Where did we mess up? After reversing it again, it's correct. It's the reversed answer that's a little wrong. Oh, oh no, oh no. The first element and last element will change after I've done the reverse thing. Oh no. After I've done a cyclic shift, they will also change. Yeah, that sucks. I think we need to keep track of the actual array. The problem is that this can exceed the time limit. We need to keep it smartly somehow. We can keep a deck, I guess, and a variable telling whether it's reversed or not. Okay, we have a deck. We put, I can just get rid of these. Let's just do d dot pushback. Okay, I need a boolean whether it's reversed. Okay, let's make, let's flip this. Okay, now if it is reversed, then I want to pop, and then I want to push front, otherwise I want to push back. Else I will just push back. Okay, now here first element equals, let's say, d dot back and sorry, d dot front, and last element is nothing but d dot back. But if it is reversed, then we swap. Okay, so this is fine. I think the problem, however, is that we need to actually do the cyclic shift. So for that, we take the last element, we pop it out and push it to the front. So if reversed, then we do d dot pop back, sorry, pop front, and d dot push back uh, last element, whatever it was. Else, just the opposite of that, d dot pop back and push front. Push front, yeah. Still a little bit wrong. Oh wow, even after all this, how's that? Wow. How about if it's reversed, then I push it to the front. If it's not reversed, then I push it to the back. This is the first element, this is the last element. If it's reversed, then we swap. If it's reversed, then last element is in the front. So we pop front, push it to the back. Is that what we do though? We want to take the last element and put it in the first place. Yeah, exactly. Let's maintain both the answers correctly. And len plus plus will definitely do. We push it to the front, then this will be like this, and this will be like this. Right? Makes sense. I don't do this anymore, we just say that it is reversed. What about this case? I say we don't do anything with this. We don't do anything with these. Yeah, that's it. Just trying to simplify the implementation so that it's easier to find any bugs if there. Oh, sorry, temp. Okay, cyclic shift. Here we go. Even more wrong. Nice. S equal to 2 just makes it reversed. If it's reverse, it makes it correct. We either print the forward answer or the reverse answer. If it's reversed, then we push it to the front. Forward answer gets changed this way. Reverse answer gets changed this way. I think I don't really understand what reversed means. How will forward answer change when it's reversed? Wow. Why don't I keep two decks, one in the forward direction and in the reverse direction? No, because that will be more hassle. But yeah, fourth element is wrong here. Fourth is just this operation. 1. That's wrong. Okay, why didn't this update the answer? We have to update the answer here, right? Do a cyclic shift, we have to update the answer, right? The temp is the element that is moving from last place to first place. So okay. Okay. If this is the case, temp went to the first, so subtract len minus temp as here. If we just add len times temp. No. How will that work? It's 1 plus m times b1. Okay, when we add it, we get 2 times last. We don't have 1 time anything. That's the problem, right? How do we keep track of the correct reverse answer? We have 1 times b1 plus 2 times b2 plus 3 times b3 and so on. If we take this element here, so we also have m times bm. When we take this element here, we just add b1, b2, b3, bm to this thing, and it becomes 2 times b1 plus 3 times b2 m plus 1 times bm, and we subtract m times bm, then it becomes 1 time bm plus this thing. So that's the cyclic shift. But how does the reverse work? So let me write the reverse coefficients for this. So this is m, this is m minus 1, so on till 1. Now if this goes here, I think we have to subtract the sum and add this value. That's how it should work. And then we can simply copy. I think just changing these should work. Wow. They just sort of switch roles, so I think it should have worked, and I guess it did work. Yeah. That took longer than it should have. Okay. So they've given us some Python code. This was clear, right? Wait a second. Just keeping track of whether I kept a deck to always keep track of the first and the last element. Did I ever need the first element though? Probably not, but still I needed a deck because I can insert the elements in any direction, and I always need to get the last element. I never needed the first element. Wow, this was just confusing. Okay. So I was trying to do this without pen and paper, and that's why it was getting hard. Simple. Writing it down often helps. That's what we learned here. Anyway, so we have Laka, Vaka, Saturno, Saturnita, something. Okay. There's a function, there's an array, there's a length n. Okay, so we already have a and n. And for every query we get k, l, and r. Okay. So to solve a query, we will get k, l, and r, and we'll just loop from l to r. Now, while k is divisible by ai, we keep dividing k by ai, and at the end we add the remaining to the answer. Okay. So I think it's obviously n square, q into n solution is, I think, very, very simple here. Just do the iterations and you're done. You kind of have to do it fast. So we know that this operation, k being divided by something, cannot be done more than logarithmic number of times. If we can just quickly find the next element in this array, which is a factor of k, then I think we're done, right? So yeah, then that's done. So that's all we have to do. For any k, we need to find its next factor in the array. Like, at least right now, that's what I'm thinking. The problem that we have to solve is you are given an array, you are given an index, and you are given a number. So you want to find the next element, which is a factor of this element. Are they unique? They're not unique. Right. So we can sort of iterate on the multiples, I guess. Probably not. We can know every factor. Can we know every factor of k? We can technically know every factor of k, yes. We want to find, can we iterate on those? It's cube root of 10 to the power 5 multiplied by 5 into 10 to the power 4. So I think we can iterate on every factor of k, find the next one, but that's just one step. Probably not the right idea, but maybe we can explore in that direction later. We can maybe do it with prime factors. So we can do the prime factorization of k. Now we have all the prime factors of k. And we want the first, or we want the first number with, no, we want a proper divisible, proper divisor, not prime factors won't help here. We can iterate on all divisors of k, or we can iterate on all multiples of ai, but that won't work because these are not unique. Otherwise the number of multiples is not too high generally. We can still iterate on all divisors of k for every query. Four seconds. I think that's what we have to do. Because why else have they given us 4 seconds? Just iterate on every divisor of k for every query. Just iterate on every divisor. Find the first one. Find the next index. Probably not, because there's a log also there, right? That's the problem. I don't know if the logs there or not. It's cube root of k multiplied by number of queries multiplied by, I guess, log of k. I don't know if this will work. So this is less than 100 multiplied by 5 into 10 to the power 4 multiplied by, this is, I don't know, 18, I guess. Okay. So this is 5e6 multiplied by 18, or 90e6, which is 9e7, which is less than 10 to the power 8, and it should work in 4 seconds. Yeah, technically this works. It does work technically, but I feel like it's an ugly solution. I don't really like this. Cube root k times log k. This is 1800. 1800 is 1.3. 18 times 18e2, 96, 97. Should work. Like, I don't like this solution. I want to iterate on all the multiples, all on the divisors of k. I think that's the only thing that works, right? Like till now, that's the only thing I can come up with that actually works. Okay, let's do it. Now, we also need to find the minimum index after a given index. Probably can't. Because that's another binary search that I don't want to do. I was hoping we can find a clean solution here. I don't like even if I could sort of do the one I was thinking about, I don't really like that. I don't want to do that. I want a nice solution here. Maybe we can do a square root decomposition sort of thing. The factors of k that are greater than the square root are not a lot, and then all the others are pretty small. For the big ones, I can maybe do something else, and for the small ones, something else. For the small ones, I can maybe directly keep it calculated, the next index. That works sort of. But what about the big ones? Probably not. Probably not the right direction. I need to quickly get a divisor of k that lies to the right of the array. So what if we move from a right to left direction on the array and keep track of that stuff? What if we move on this array like this? What if we move like this, and keep track of the last occurrence of every divisor? Does that work? Not every divisor, but like we can actually keep track of every element till now. That makes sense. That makes sense. We can also get like from value till to index, I think pretty quickly. For any given value, find the next index of this, just a binary search. So this is just log of n from value till next index. So maybe we can just find the next value, but it's actually the nearest value. Nearest divisor, that's the problem. Like if we have 15, we need to find the nearest 3 or 5 or 15 here. And if we move from right to left direction, might be better, because when we come here, we can sort of already know what all is present. If we have 3 here, can we find all the multiples of this here? If we take this fact that 15 is a multiple of 3, if we make this sort of an edge, there are only, like, there are not a lot of these. Like total, this will just be 10 to power 5 log 10 to power 5 such as edges. So for every one of these, we can maybe resolve this in some way. We can do a matching. We can update this. We can maybe update all the 15s with all the 3s. For every, find all the 15s and go to the next 3. For every 3, there can be a lot of 3s or there can be a lot of 15s. That's the problem, right? Which one do we want? Do we want to get 3 from 15, or do we want to get 15 from 3? That's the interesting part. Can we do a binary search to get the first index that has a multiple? Each index find the nearest multiple. Sorry, nearest divisor. How do I find the nearest divisor? For any index, find the nearest divisor. Iterate through all divisors and find the nearest index of one of those. Like that. Actually, it's not even this. It could be a random k. Find the nearest divisor. We can sort of go to the past. If we were at this element, can we update all its multiples? But the problem will be there can be a lot of 3s in the array. So what if we had all the 3s in a vector? Like all the indices of 3s in a vector, like we have 0 and 1, 2, 3, 4. Okay, so I know all the places where 3s are present. Now if I iterate on all the multiples of 3 times this, can give me a daily already. How many submissions? 329. Shouldn't be as hard as I think it is. Just about finding the next divisor in the array. 215. Just this. Yeah, finding the next divisor will definitely help. Just 5 is the answer. Yeah. In case, yes, restart. 6 is the answer. Yeah, works. Just need to find the next divisor of any number in the array. Mm, is that a standard problem? Given a number and an index, find the next divisor. I hope it's not too easy. So let's say we don't have the index is always 0. So now it's like given an array, just find the first divisor of any number. We can maybe store the nearest position of every number. Hmm. Then iterate on the divisors of this. Okay. And pick the minimum of these. Right, so we have cube root k divisors. This is also binary search. It's actually less than 100, but maybe like 90 or 80, maybe like 80, I guess. Right? What's 8 cubed? 216, yeah. It's like maybe 80 something. And these are 18s, but yeah. So it's 5 times 10 to the power 7 times 16 times 2, or we can do this 10 or 10 to the power 8 or 1.6 into 10 to the power 9, which shouldn't work. This is not exactly log k, but and it is 4 seconds, so we can take that risk, but I don't know. I don't know. Trying to think of something else. How do we find the next divisor of any number? Do we really have to iterate on all divisors? I really don't want to do that. Something like 2, 4, 6, 8, and so on. If that doesn't work, then a number of steps get reduced by a lot. sorry, 2357. If that doesn't work, then steps get decreased by a lot. So if this is high, then this will be low. What about this? This will be high. No. Okay. One of these numbers can maybe have up to 100, 200 devices. Plus. But they have given the queue to be a little small and they have given a lot of seconds to us. Probably they want us to do this solution. I don't like this. Can we do something a little more efficiently? Probably not. This part is definitely fixed and we have to do it per query. I can maybe get rid of this. Probably not. I can maybe get rid of this one. Not sure though. To move from left to right, so probably not. Ah, this sucks. Can I not get rid of anything here? Okay, let's try this. I give up. I'll just try this solution. I don't like it, but I'm gonna try it anyway. So I need to find the divisors of A quickly. This loop works in n log n, by the way, like capital N log n. Okay, now I have all the divisors of any number. Okay. Fine. Oh, sorry. Now I want, by the way, let's do, so that I don't forget it later, L minus minus R minus minus. Okay. Yeah. Now it's just, I guess, positions of AI dot pushback I. At the end, I do want to clear this. So I'll do positions of X not clear. Okay. Fine. So that it works across test cases. Okay, now I have the position of every element. I also have the sort of divisor, like the divisors and the positions, everything I'm having. I can just do a simple binary search to find it. I really don't like this. I don't have another option right now. Okay. Hmm. Let's just do answer equals 0, see out answer. While something, maybe while L is smaller than R. I don't know. See. Hmm. So we want the first divisor. Okay. So we can iterate on the divisors of K for int X in the divisors of K, I guess. We do have to iterate on all of them so that we can find the minimum. This won't work. This will never work. But still, let's do it. Hmm. Okay. I don't know. Let's just say this is R plus 1. So we have to jump till next. Okay, then actually divide it, because what else can we do? So that not found, next minus 1 equals r. Okay. If nothing is found, the whole range is just add this, right? That's it. Yeah. Answer is also a little bit wrong. In the second case, mhm. Mm, okay. This is inclusive. This works, but probably will give TLE because the time complexity is not good here. It's not good. I don't know. Wrong. Wow. What am I doing? I have the devices and the positions. I clear the positions. I push the positions. I try to divide it by A, L. Find the next divisor. Oh, got it. Probably this. There's not much else that can be wrong there. 249 ms. What the fuck? Ah, should I try to prove why this works? This is definitely Q times number of devices times log of K, I guess. Fuck. Fuck. This is not number of devices. This is got it. This is the number of unique prime factors, I guess. This is something else, like, you know, if you divide it by 4, but if you divide, like, if you divide it by 4, you have to do it multiple times till you can't do it, right? So they are sort of like maximal in some sense. Or, if you have a number like 25 and you can't divide it by 5 because then it will just get rid of it and it will become 1. But what I'm doing wrong here is, okay, for 1 there are no divisors. If I can't find it, then so we can get rid of it 1 by 1 if it's like n and then n by 2 and then yeah, but if we divide it by n by 2, the number is just 2. Maybe this is the wrong term, like it cannot be this small. This is like, this has to be like very, very small. This is definitely login. It is like 20, this is some number, this is small. So it worked. I don't like this solution. One reason I don't like it is because I'm not able to prove why it works so fast. This is the number of hops. Are the number of hops, like the maximum value of the number of hops is just, I guess, the number of prime factors of K, which cannot be a lot because, you know, if you try unique prime factors, then the number exceeds 10 to the power 5 very quickly, you know. Just do 2 times 3 times 5 times 7 times 11 times 13 times 17, and we're already past 500 to the power 5. So we can have at max 6 prime factors. So this value is like 6, I guess. This is 6. So it's 6 times 100 times 20 times 5 into 10 to the power 4, which is this is 5, 7, 8, 6 into 10 to the power 8, I guess, which will work in 4 seconds, obviously, but my solution worked way faster than that. It worked in just 249 milliseconds. So I think it's still wrong. One thing is that this is not 20, this is barely like, I don't know, 17. Still not good enough. Cube root of K. I really want to see the editorial why this works so fast because I'm not so sure. I did have this idea a long time ago, but I didn't want to implement this because I wasn't very confident at this, but it works way faster than I expected. Why have they given 4 seconds for this? Generally, how much time people are doing it? Okay, 249 seems pretty common. The people are able to do it in 100 milliseconds. But I am one of the fastest. Like, among few of the fastest, I guess. Yeah, I am a human, bro. How was I so fast? Doesn't make sense. I do get that, like, sort of, once you find a factor, the number becomes smaller, so the cube root of that also becomes smaller. So I do get the idea that it will work faster than I think it will. Maybe it's not, like, instead of 6, if it's just 3, 8, then yeah. Then also it should take like 1 second. Approx 1 second. 300 number time, it takes around 1 second. No idea. But yeah, this was the best solution that I could think of. So I implemented that and it's way faster than I thought it is. And now what I'm confused about is why did they even give 4 seconds? Like, what's the worse solution than this? Can anybody let me know in the comments if you were able to, solve this in maybe 3 seconds or something? Did they give 4 seconds time limit just to, give us the confidence that this n log k cube root k times q solution will work? Q, uh, what was the so this was the pessimistic estimate, but obviously this value, like, it's not actually log k, this is around 6, and this is cube root k, but not all 6 times, because after one of these it's like it has to get at least half, then 1/3, and so on. So maybe it's, I don't know, maybe this whole thing combined is cube root of k times maybe 2 and not 6, and this is not log n, this is again around, this is around 17, but each time it will change. So maybe, like, my estimate was like maybe too pessimistic. These are the worst of the worst numbers for each of these. The queries are independent though, so q times something, a product of these three, such that all three of them can never be the worst. So it's like, if this is bad, like if this is 6, first of all, this is not log k, this is close to 6. The number of unique prime factors a number needs to kind of exceed the 10 to the power 5. So this is around 6, and like when this is 6, this can't be that high every time, and like when this is changing, this can't be high every time. So I think one average case could be like, what if this is always 1? So if this is always 1, then we still have cube root k times actual true log n. So then this could be 17 times 100. But actually not really. This can't be 17 times 100 also. Because these are different points, and then all of them can't be, it can be like this maybe at max. Right? This is just a constant. This is log of 100 minus log of 100. 17 minus log 100. This is what? 5, I guess. So it's 12 times 100. 1200 times 5e4, or 600 times e5. 6e7. Yeah, now this makes more sense. Yeah, I think it's very hard to figure out the exact time complexity here. But even with the pessimistic number, it seems like 4 seconds are enough. So you can try this out. So yeah, that was this contest. I really fucked up B this time. But yeah, see you next time, and do subscribe if you like these videos. Oh, sorry.